Please welcome Mikael Tonnberg. Mikael is CTO at Carbon Cloud, a company that calculates the ecological footprint of food products. He has been working with startups over the last decade and loves fast-moving companies. Mikael is also an outdoorsman, a hiker, and a bushcrafter.
Great. Yeah. Thank you for a nice introduction. Yeah. So I work at Carbon Cloud, and today I want to talk about why we use strongly typed functional languages. And we are we are a scale up, so we grow quite quickly, both in number of people and in the application as well. So a lot is happening at the same time. So first off, I want to kick this off with that our choice of use strongly typed functional programming languages is a business decision. And I hope I will explain why we took that decision and the reasons behind it. So I hope that this talk will be quite inclusive because I think if more managers would know about these benefits, it will be a stronger push for these types of tools. And I think that will be beneficiary for everyone. So let's get started. I get this question a lot. What's the benefits, for example, of Haskell and other languages? And I think it's, while a valid question, and I think it's a natural question to have, I think it's the wrong question to start with because it puts the conversation in a context that's quite hard to get out of. And usually the answer is focused on specific techniques or tools or like immutability or other stuff that is quite hard to like correlate with business benefits. So I would instead want to start with what we want to achieve, which is very high concept, but I hope we can get down to the nitty-gritty as we go. So what we want to achieve, in essence, right, if we talk about software, we want to get a working application, whatever working means. And one way to think about it is that we have a mental model in someone's head or as a team, and want to transfer that to the computer so it can run the code and serve other humans, right, or other computers. And another name for that mental model is the domain knowledge and the domain requirements, how it should work. So since we have a working application when we have successfully transferred the mental model, we can express it like this. We have a working application when we have successfully and completely encoded the domain requirements and the domain knowledge. That raises a couple of questions, of course. What is the domain knowledge and how do we encode it? And how do we make sure that it's complete? It's also complete and both today and tomorrow, right? Because the domain is not static. Usually it's, especially if you have a SaaS product, you add stuff to it and remove if you're lucky. So to get that more as a formal starting point, when we do programming, we want to capture the knowledge about the problem and in a way that is understandable for both the computer and humans, because the computer is going to run it, right? And the humans need to be able to understand to make changes, both now and in the future. And I think especially the last part is really important for a business, since in our case, as we grow, or in other companies that are quite large, the information have a tendency to get lost over time because people quit or just change positions or change teams or forget because we are human. So if this is what we want to achieve, we can take this further. Okay, how can we do that? And this is a quite intense image. It doesn't matter if you don't understand the nitty-gritty, but the point is that most things that is domain requirements, can be declared quite easily, even though it's hard to implement or hard to enforce. So here, I don't know if you can see my mouse pointer, I hope so, but in the top we have a API call to get at most three animals that lives on the savanna. And here in the bottom, we can see that's we have the end result that we're going to return. And we have a domain requirement that the user should have access to that habitat that we are asking for, in this case, the savanna. And that is something everyone can understand and declare, regardless of how hard it is to implement. So that is an example of domain requirements that we want to capture. So if we dig a little deeper, why do we want to capture knowledge? Yeah, so I touched upon this already. So in a project, when a project starts, usually have a phase where you collect a lot of information and you learn a lot as the project goes on, right? And that is quite common, that the organization loses knowledge, or that the knowledge is concentrated in a few key individuals, which is bad from an organizational standpoint, both because newcomers or other team members can't bring the full potential to the problem. And of course, there is single point of failure, right? If that person needs to go to another project or just become a bottleneck time-wise, because it needs to help with other team members or change jobs, whatever. Or even if nothing changes in the team, we still forget. So we want to capture that someone that survives these kind of changes to enable the business to live on. And if we capture knowledge and make the computer understand, in this talk I will use the word understand a lot. And of course, as of yet, computer doesn't understand anything, but I will use that word to describe that we have successfully given the information to the computer in such a way it could take action on that information in the way that we want it to do. So if we make the computer understand the domain knowledge, we can make sure that it's enforced. We can get help by the computer. And because when we develop our business and we get new either features or we update the domain requirements, as in a non-trivial case, usually our addition will create ripple effects, not in code. It could happen in code as well, but in the domain model with existing parts. So you have an old part that functioned in a way before, and now then you add a new concept that will affect the old one. And for a more complex domain, that could be really hard to reason and understand as a human how all these things are interconnected. But if we can capture that and let the computer help us with all that relationships, we can design new features the best way. And as I touched on already as well, who can access what is really critical, especially it depends on the project, of course, but for I think most systems have some part of the system that is not for everyone. And that is, I think, a key thing is to make sure that the data can't leak. Continues, yeah, so if we have captured knowledge in some place that's accessible for everyone that's outside people's heads, it makes onboarding much easier because we don't have that bottleneck. I guess quite many people can relate to a memory I have that I was quite new in the industry and I worked the system and I just did a change, and then a senior developer came in. Oh, you can't do that. You need to change that thing over here as well, because other things, everything will just break. And that is impossible to know unless you just work the system for a very, very long time. That is very hard to remove completely, of course, but if you can reduce that as much as possible, it will be a more healthy and more sustainable team. And over time, it's quite hard to know what the organization knows and you when the decision was made. And if you can capture that as well, it's easier to make new decisions. And I think that one of the key things is, since many problems are easily declared, it's easily shared. And you can use the same language, even if you're a developer or you're working on the business side. So that makes it, because one key thing is, of course, to build the right thing for the right person or the right user. And all of this avoids bugs, and it's easier to make right decisions when you do the nitty-gritty coding as well. And this one, I think, is both for me personally as a developer and also on organizational level, is if we can remove time spent on defensive programming. And defensive programming is that when you don't trust the rest of the application. So when you write a function, you need to double check all the things, all the inputs, to make sure that they live up to your standards. And then you send yourself call another function, and that function also needs to check because it doesn't trust the rest of the application. And that creates a lot of noise in the application, and also makes the code harder to work and reason about. So what is knowledge? Then more specifically, I used quite broad terms. So in general, or like in a high level, it's the information that we have currently that affects our choices, how we write the code and how we design the code. And that could be all from like security, or how the who should do what, or how the blue button should work, and everything that can be collected into this bucket of knowledge. This is, of course, applicable to many areas, but we will focus on application code specifically today. So more concretely, for example, what kind of inputs are valid or expected? What can the output be? And here you can be very, very general, but the idea is to be as clear and succinct as possible. I will go into details more about that later. What can go wrong? When should this code be used and when should it not? When I run this code, do we create some other side effects? Do we update something in the database, for example? And the last point here, I think is really important. I think one that can generate a lot of nasty bugs that could go under the radar for a very long time is, how does similar domain concepts differ? Here I have a theoretical example of a user with admin rights and an admin user, for example. And those similar objects can have a really key differences, but can easily be smushed together and create both security risks and other bugs in the system. So how is knowledge best captured? Let's talk about excess code. There is infrastructure as code and configurations code and a bunch of others. And I think they have a lot in common is they focus on being declarative and focus on the outcome. And I think that there are several benefits. And one is that it is easily understood what we want to achieve, and then all the details can be left out, and you can reason about the high level things, the outcome. And knowledge as code is our approach to capture knowledge. It's language and platform agnostic, and I will talk about, but some languages and platforms are better at it. But I think we started with what we want to achieve, and okay, we want to capture knowledge, and how do we do that? So knowledge as code, to give a good foundation, we use a couple of like fundamentals that we use to in different techniques and tricks that I will show you later. So knowledge should be declared once and enforced globally. It should be complete, precise, symmetric, and unobfuscated. I will go through each and one of these. And together, they make sure if we fulfill all of these to 100%, which can be really difficult, impossible in some cases, and depending on languages, then we know that we have reached very, very far when it comes to capturing knowledge. So first, declared once, enforced globally. It means that we should have a central place where we declare the wanted domain requirement. For example, that the settings page should only be accessible by admin, for example. And that means that even if the code base grows very vast, the knowledge about the requirements stays very, very small, and changes to the domain can be easily reviewable. And then if you change it, you get ripple effects, but then you can take care of that like more in a mechanical way. Yeah, so it's reviewable. And if we declare it, we want to enforce it, because humans are really bad at this. And if we don't get help with it, it means that the domain requirements more will be emergent property of the code base more than to have something that we want to have declared the outcome, and then we write something to match that. And so if we get help of the computer, we can focus on things we are good at. And the computer is also very good at pointing out conflicts in our mental model. I said at the start, we start with this mental model and want to transport it to the computer. Most often than not, that mental model has flaws or conflicts that could be real hard to spot as a human. But if we use the help of the computer, we can get help to resolve those conflicts. It should be complete, means that all valid values should be representable in the code. So if we want a really large number, we shouldn't use int32, for example. And all known unknowns should be explicitly expressed. For example, we might not have a number here, or we might not have a result, or this could be either, we should be maybe a list, so it could be empty, or so, but it's really to bring all the known unknowns up and show them to everyone is really important. Another way this applies also is that if a function can fail, by fail, I mean to not be able to do the job that it wants to do, the computer should force you to handle that failure case. And better yet, to change it so the failure case can't occur, right? A complete is usually quite easy to achieve. Precise is usually a bit trickier, and that is the only valid values should be representable. So example, if I want an integer, a positive number, I can say I accept all integers, but then of course I can get things I don't want. So precise means that I get only the things I want, and complete is that I get everything I want. And precise also means no overlap. So when we describe something, and in the words we can have either this or that, for example, those two options shouldn't have any overlap, meaning if we say I have either a list or a non-empty list, that is not good, because all non-empty lists is a list. So that means that they are not really two cases. And it should be symmetric, meaning that all knowledge that we have should be available to both human and computer, because humans must, of course, understand the knowledge to be able to make changes, and computer must understand the knowledge to be able to enforce the rules. And feedback from the system should also be given to both sources. And when something goes wrong, the computer should try to help the human to address it. Unobfuscated is we should use abstractions without knowledge loss. Here I use a bit loosey terminology, but instead of, if you take the whole code base, there are limited options. For example, if you say I have a bird or a cat, and if you use, for example, in Java or whatever, and have an iAnimal interface, if you take in the whole application, you know that there is only two instances of that, a bird or a cat. But could be very, very hard to analyze and understand when you work with an animal. So it's much better to just say you have an animal, and that could be precisely a bird or a cat. And if you add a dog, you need to, everywhere where you don't care about which animal you have, it doesn't matter. But all the cases where you do have specific behaviors for different animals, then you need to take actions. And then the compiler will help you find all those areas. or you should use general, well-defined non-domain concepts that is not just made up, such as list, dictionary, functor, or monad. So with this foundation to be declared once and enforced globally, complete, precise, symmetric, and unobfuscated, the question is, how do we get there, right? When we look about tools, there is both capabilities, that what that tool is capable of, and how expensive is it to use it. And here you might have noticed that I nearly assumed that we going to have a compiler. And I think as of today, that is essential. If we find any other way to do it, I think so then it's fine. But I would say that this is the only practical way to do it today. And which tool you use is depending on team and project, of course. Now I'm going to show you a graph that is and of course, depending on which tool, you can get different bang for the buck. This slide is not meant to be precise or show the exact details, but just to illustrate that if we have the cost of use, the cost on the y-axis and how much knowledge we have captured on the x-axis, we can see that different languages have different max of how much knowledge they can capture. For example, C# and Java they don't have capabilities to capture that much. And different languages have different amount of costs when we try to capture a certain amount of knowledge. Again, this is not meant to be very exact, but to give you this map of different options and where you can put it. Of course, there's other considerations to take into account when choosing a tool, and that it could be the tooling or the ecosystem and so on. But this is just one way of looking at it. So soon I will get into the more concrete things that we use in a daily basis, but just to build up a bit more foundation first. So if we focus on the symmetry part, some things humans understand and some things only machines understands. And it's important to find techniques and that works for both parties, right? That is accessible for both, because otherwise we can't have this cooperation between man and machine. So just to give a few examples, machine code is practically not accessible for humans, or relations in vast data sets. That can be very, very hard for a human, or impossible for humans to do. For example, in a big code base or a very large data set. And human only, like stuff like comments or example in a comment, the name of a class, function name, variable name, record field names, the tags for liquid data types, or the value level of understanding is more or less not accessible for the compiler, with a few examples in different languages that are more outliers. So since they are not enforced and checked by the computer, both they're potentially false. If you call a variable deleted user, for instance, that has no relation if it's deleted or not. And they can rot over time, since if you have a comment, that's very common that you have a comment and then the implementation changed, the comment is just outdated. And there are also victims of game of telephone, meaning if you have something they called admin user in one function and you send that variable into a second function, and in that function it's called user with admin rights, and you send that, you pass that on to a third function, and there is called just user. Nothing in the actual value have changed, but the perception from a human have changed quite greatly from an admin user to just a user with these steps, right? So what works is types and function signatures, and in a certain way test as well. But let's go back to tests in a bit. Before, I just want to say it cuts both ways when it comes to symmetry. And I say many strong and not so strong compilers are not really focused or have achieved good feedback that humans can take action on, partly because it's a very hard subject and I don't pretend I have the solution. It's a non-trivial problem. But as an example, Elm focuses on a lot of solution-oriented feedback, all from technical things to just, here is the URL to the Slack room, you can go and ask questions. And just to take an example that is not technical, but I think encapsulates some of the feedback I get from Haskell sometimes. Size of sulfation plates prohibits needed chemical interaction instead of time to change the battery. And it could be good to have that really concrete technical information, but in most general sense, it's just you forgot to add the last variable or the last value at the end of the function call and so on. Again, I'm not saying that this is an easy there is an easy solution to this problem, but I think it is a problem. So let's talk about tests. Are you writing tests to capture knowledge for the future human reader? And if that's so, will that person have practical access to that knowledge I try to encode? Or could it be described in a more declarative and general way in the types? Are we writing tests to make knowledge available to the computer? Or are we using tests to help with the initial development? And I would say there's quite a lot of problems with tests. The first is they are incomplete. If you just if you have add and then you say add 3 and 2 together, it should be 5. That doesn't really help the computer to extrapolate that information. In my experience, you might have an other experience, but in my experience, tests, especially when you have a vast test library or a test base, they're not really good source for knowledge. They're really good to reactively catch problems when you change something that you shouldn't have. But since they're incomplete, they might miss things, right? And I would say it's hard for the computer to understand the intent when you say that 3 plus 2 should be 5. Or especially if you have your test library have a naming for the test that entails information that won't be accessible to the computer at all, right? And it can create a false sense of security, I found. However, I say test is still very much important, and we write a lot of them. And I think there are, for example, property-based tests or fuzzy testing can alleviate some of these problems, but they are still a way to just generate a lot of tests, right? Here's like a rough graph to try to capture this, that we have different ways to achieve knowledge symmetry. And when we have high levels of knowledge symmetry, both the computer can do a lot of much more work for us, and humans can understand the knowledge that are encoded, and the organization is more sturdy because of it over time. So if on the left side we have comments that doesn't really mean anything and can rot over time, we have example tests that can fail. The computer can at least run it. The property test is a bit better, but if we move it to the types, we can close loopholes completely, and we can be a more complete description overall. So some examples that we use like quite often or daily. One is so the idea is to do stuff that we can move things up that ladder towards more and more knowledge symmetry. And one way to do that is to have doc tests. They are in different languages, in different iterations. And that is that if you have a function or method, you can have an example in your comment to say that add 3 plus 2 should equal 5. And the problem with that is that usually the computer can't access those examples because it's just texts, and they can't check the validity, and humans will extrapolate the example correctly or incorrectly and expect a certain behavior. And the example is not usually syntax to compiler checked. So if you just copy that and you try to use it, it might not run, right? Because either it was wrong from the start or the actual code is changed over time. So this is doc test is a way to try to bridge that or make it not so bad. So here's quite a lot of code, but it doesn't matter. We have a function called map. And over there we have an example called map, and we send in 2 arguments, and this is the result that we assume to come out of it. And this is run either by when we build or run tests. So that means that we have moved this example up the knowledge symmetry ladder, which is good. Another technique that I think is really useful, and I use it a lot, and I think that is one of the key tools, is to combat name reliance. And it's, in a general sense, try to avoid names, for example, variables or functions, to understand the code. For example, on record field names or variable names. And one exercise you can do is try to removing those labels or comments and see what happens. So here we have a car, and it's a record with brand, owner, and model and owner, which is very clear. But if you see that the type is a string, and the exercise is to, okay, what if we just remove those 3, and we will get this in the middle, string, which is very clearly non-usable. It's really hard. It's easily to be flipped, and it's easy to how can I know which one is which, and so on. So, okay, can we make that from a string to a type, brand, model, and owner, and suddenly it's very clear what the 3 values are, and we can let the compiler enforce that we use them correctly, right, all over the code base. Then for some certain reasons, you might want to convert back to the record for other reasons. But I find that doing the exercise is a good thing. It usually makes it very clear if you haven't captured enough knowledge. And if you use records and other things, it is easy to use this as aid, and therefore not focus enough on the types, because it's really clear for a human when you look at this, but it's not very accessible for the computer. So I see these kind of record fields to be comments. I would say that that's the same thing. Here's another example that we can look at with the fundamentals that we went through. Let's say we have a text input from a web page with the email. We could just say that is a string, but then we say that, okay, if it's a valid email, we want to highlight this submit button, and if it's not, we want to show error message. So it could be either a valid email or an invalid email. Here we have several problems. We have that it's valid email just holds a string, and not every string is a valid email. So we try to fix that. So we say a valid email is an email, and then we have an invalid email for everything else, right? Then we have the problem with preciseness with overlap, because you can still express a valid email in a string. So the next step is to say, okay, we have either an email or an invalid email. And again, you can see that these tags loses their importance, which is good. Other examples, parse don't validate. There's a great blog post. I should have linked it here, but you can find it. That also is a very good technique that fits well with these things. There is a library in several different languages called Ghost of Department Proofs, which is really good, or type-driven development in general. So back to the beginning. What's the benefits of these kind of languages? It's that we can capture a lot of knowledge at a low cost. And that's the reason we see that all of these things to capture knowledge is very important. And then we've chosen a tool that can do it for very low cost. And that helps us with the rapid growth for the reasons I described. And we catch things early, which is good both from a user perspective, because we don't let out bugs in production that often, but also it's less expensive to fix it earlier than later. There's a famous graph that shows how expensive it gets if it goes out in production. This allows for aggressive refactoring. We've changed our code base quite a lot over the years without any regressions. And as I said, a very key thing is to include non-developers in the discussions to make sure that we build the right thing, which if we build the wrong thing, it can cost a lot of money. So therefore, it's a pure business decision. And I think a weak knowledge as code capabilities would be a sincere business risk for us. So to just end off with a few challenges that we've seen is that information is not knowledge. So even if you try to encode a lot of things in the code, if that is not easily accessible for a human, it's something. For example, if you have a vast library and if you can't read, you don't have, it doesn't matter. Or if the library is totally in disarray, even though if all the books are there. So that's something we need always to improve on to make sure that the knowledge is as accessible as possible. And that doesn't mean to remove the knowledge to make it easier to understand but you misunderstand because not all the knowledge is there and therefore do mistakes, but to keep all the knowledge but make it easier to access. And the other challenge is that it sometimes is a daunting onboarding experience. It's good because you can more easily start working and you understand when you have made something that goes against the current domain requirements, but it can be quite daunting to discern if should we change those now when I change the other things. And in essence, this is a very good thing because we catch a lot of things, but it still can be quite daunting when you start working in the code base. Cool. That was it.
Thank you, Mikael. And yes, we will move to special chat for the Q&A. See you there.
Yeah, super.